Welcome to the demonstration of the Myers Engineering Mini Vacuum Mixer. Today we are going to be demonstrating the benefits of high-speed dispersion, the difficulties in air entrainment, and how this product removes the air. For this demonstration we are using an electrician's conduit lubricant for pulling wires. This material has some viscosity and body. It tends to retain air, as you can see, quite easily, which makes it, and being that it's clear, makes it easy for us to demonstrate exactly what's going on in your mix. I'm going to begin the operation of the mixer, let you watch the material move. Now as you speed up the mixer, what is happening is the disperser is pumping the liquid out against this section, this wall of the container. The vortex then breaks in two places. It goes up and back in, and it goes down, around, under, and back in. You'll see that it's got some forward motion, and it returns to the center of the blade where it then is again centrifugally pumped out. Increasing the speed. Okay. At this point right here, I'm beginning to open a vortex. You can see the funnel-like shape coming down from the top. Now this is typically where most people are going to add their fillers. The most common filler, and the filler that we're going to talk about mostly today, is Cabicil, which is the brand trade name for Cabot, otherwise known as fumed silica. Fumed silica is a very light material. When you introduce it, it tends to take air with it. It's usually 50% silica and 50% air. That material will fall down into the vortex and begin to meet the high shear zone where it will be blended into the fluid. Now I'm going to increase the speed slightly. You can see the vortex starting to open. The vortex has now reached the hub on the disperser blade. I continue to increase the speed further. What we are doing right now is we're getting good agitation, however, no actual high-speed dispersion or grinding is taking place yet. As I continue to speed it up, you can see the shape of that vortex. It's beginning to widen out at the bottom. In just a moment here, that vortex is going to meet the blade. And when it does, we will be starting to achieve better dispersion, but we will also be beginning to entrain air. Without vacuum, something you can't avoid. Again, take note that if you watch the bubbles that are in here, they are moving out to the side and then they come right back in and hit the high shear zone. Okay, I'm going to go ahead and open up the vortex now a little bit further. And now we are starting to reach actual dispersion speeds. At this point, most people are going to be pouring their Cabicil in quite quickly. Going to be continuing to add the Cabicil. Okay, and now they're going to begin the high shear phase. And this high shear phase inevitably is going to put air into the product, like you can see happening right here. Typical dispersions where particle size reduction is achieved happen at close to 5,000 feet per minute. Introduction of most silicas, however, are done in the neighborhood of 3,000 feet per minute because you are just trying to achieve a good mix and do not necessarily need particle size reduction. Okay, so again, this is simulating what happens in the dispersion process. We have a nice vortex on the top. We are doing adequate mixing. Okay, I'm going to go ahead at this point and I'm going to stop this mixer, assuming that if you were adding silica to a resin, you now have achieved a good homogeneous mixture. Some people may choose to run longer, which is going to probably only put more air into the batch. Slowing the mixer down. See a few bubbles there. Now the product is very white in color and nearly opaque. Those are micro air bubbles. The air bubbles, along with the silica, would have been dispersed into the fluid at this point in time. And the bubbles were torn apart by the high shear and made very small. This is a problem because upon settling they will not just come out. In a composite application, this air would represent an absence of resin and therefore a potential weakness in the material. We are going to now show how this air can be removed by starting a vacuum pump. We are starting the mixer. We are beginning to pull vacuum. As you pull vacuum, you're going to notice that the product is going to start to rise. You must be very careful, because if you pull full vacuum right away, the product will rise all the way to the lid and it will suck down the vacuum tube, blinding your pump and creating a mess. See the product rise? I'm going to let it rise up just a little bit just for the effect. Let it go down. Let it rise up. It is rising because the air bubbles are expanding as you pull vacuum. Now, typical dispersion, if we had added the silica and then pulled vacuum during the dispersion right away, this process would be very quick because you wouldn't have put the air in the first place. But now that the air is in, we have to see to it that it gets out. So we're going to let the mixer run for a few minutes and let the air come out the top. You can see that, possibly you can see there's some bubbling coming off the top. One of the things that we are going to notice when we're done is you can see a little condensation up here. This material does have water in it. The shear from the disperser puts energy into the product. The energy in the product will cause the moisture or the water to turn to gas. So when this is done, we will see a few bubbles. That is not air. That is just moisture vapors. And as the material cools, those will go away. But we're going to go ahead and run this for a few minutes. Currently, we are pulling 27 inches of vacuum. Better vacuum pumps are available, which would make this process go a little quicker. Full vacuum is closer to 29.8, 29.9. Again, you can see the vigorous action in the high shear zone. You can see the splitting of the flows along the wall of the tank. One of them moving up, one of them moving down. One of this, I can feel a little heat actually generating here right now. One of the, there's two principles in blending. One is the actual grinding or the particle deagglomerates, or the agglomerates that are deagglomerized in the high shear zone as it passes the high-speed blade. The second is as this material is rapidly moving underneath the material that is not moving, in the laminar flow zone, you get the product rubbing against itself, again creating better grind and better dispersion. I'm going to slow this down, see how it looks. A couple of small air bubbles. I'm going to alter the speed just a little bit here slightly so you can get an idea of what's happening. And again, for today's demonstration purposes, I do have to be careful with how much heat I put in there because the gases will be formulating bubbles when we're all done. And for the viewers, we're going to go ahead and I'm going to break the vacuum at this point in time, stop the mixer. We're going to see what we have. This process can take a few minutes, as we did put quite a bit of air in there. It does give you an idea of the problems of dispersing and air entrainment. Stop the mixer, and I'm going to break the vacuum. Actually, you can see the vapors. Go ahead. Turn it back on. We're going to watch the vapors. Actually, this is kind of interesting to see. At the top of the pot here, when I open the... There we go. When I open the vacuum line, there you go. See the vapors starting to form in the atmosphere inside, just above the batch, and they clear out. You can see this also with the change in the light. And I am extracting water through the vacuum line. So here you can see we've returned back to our clear resin stage. Most all that air that was put back in was removed. This small amount that you see here again is vapor. And we have a pure product which theoretically would be homogeneously mixed now with Cabasil or your other additives, your hardeners, etc. with the absence of air. Thank you very much.